Hi everyone, welcome to my tutorial. My name is Tigran Panasin. I decided to create this new tutorial for my students. I did create a similar tutorial on antibiotic efficacy in 2019, but I decided to create a new one so I will add more information on the statistical analysis and some additional information about antibiotics. And my students in the class conducted experiments with the E. coli and S. epidermidis, and they tested the efficiency or efficacy of 6 different antibiotics against these 2 strains of bacteria. You can see on this image that for each strain of bacteria, 6 different antibiotics were used. You can see that each antibiotic is labeled, and antibiotic is represented by a white pill, and there is uh, either a clear ring formed around a given antibiotic or there is no ring at all. In case there is a clear ring is being formed around the antibiotic, it means that bacteria are susceptible to that particular antibiotic. If there is no ring is formed around the pill, it means that bacteria is resistant to this particular antibiotic. These clear rings are called zone of inhibition. So let's start discussing first antibiotic. It's the penicillin. As you can see from these images for both E. coli and S. epidermidis, no clear ring is being formed on either of these bacteria, which means that both bacteria are resistant to penicillin, which is somewhat is not surprising because penicillin was first antibiotic being used commercially from late 20s, and most of the bacteria develop resistance toward this antibiotic. So you normally would expect this particular antibiotic be effective against S. epidermidis, but not E. coli. However, we don't see a clear zone of inhibition on either of the bacteria, which means that even the S. epidermidis evolved resistant to this particular antibiotic. Next antibiotic that I want to discuss is the streptomycin, and it is known to be effective against gram-negative bacteria such as the E. coli, and it's known to be not that effective with the gram-positive bacteria such as this S. epidermidis, and it's kind of evident with the results. There is no zone of inhibition around the pill that was placed in a plate with the S. epidermidis, and there is a clear zone of inhibition around the pill that was placed in plate with the E. coli. Next antibiotic I want to talk is the tetracycline. It is interesting to note that tetracycline is actually broad spectrum antibiotic, and it's supposed to be effective both against gram-positive and gram-negative bacteria. However, we can see here that it's effective against E. coli, which is gram-negative bacteria. However, it's marginally effective with S. epidermidis, which is a gram-positive bacteria. It's hard to see, but there is a small clear zone of inhibition around the pill, which can technically be stated as not effective, or in other way we can say that S. epidermidis is resistant to uh, tetracycline. So it was a little bit unexpected in a sense. Really good showcase to show that bacteria are evolving, and they're evolving to resist antibiotics. And next antibiotic I want to discuss is a ciprofloxacin, and it is also known to be a broad spectrum antibiotic. And we can see that there are clear zones of inhibition both for E. coli and S. epidermidis. As you can see, they're pretty broad zones of inhibition for both bacteria. They inhibited the growth of both bacteria on both plates, which is somewhat expected result. Another antibiotic I want to discuss is the vancomycin, which is pretty much a substitute for the penicillin, and it's the way it function. It actually inhibits the growth of a peptidoglycan layer, the way the penicillin actually does. However, this time we can see that these two strains of bacteria responded differently because it was introduced more recently. So the action of these antibiotics seem to be more expected. So it is, as you can see, there is no clear zone of inhibition around E. coli, which is expected because E. coli is a gram-negative bacteria, and it is effective against S. epidermidis, which is gram-positive bacteria. And the last antibiotic I want to talk about is the erythromycin. It is known to be effective against gram-positive bacteria, but not effective against gram-negative bacteria, and it's evident in the results that we see here. As you can see, there is no clear zone of inhibition in the plate with the E. coli. However, there is a pretty big clear zone of inhibition in the plate with S. epidermidis. So after measuring the zone of inhibition, by the way, the zones of inhibition are measured by measuring the diameter of the clear ring and recording the data on an Excel sheet. As you can see, we conducted several experiments. So we have 5 trials for E. coli, and we have 5 trials for S. epidermidis for all 6 antibiotics. And as you can see, the data is shown on this Excel sheet. So now we need to calculate the mean or average. For that purpose, you click on a cell, make sure to click equal sign and start typing average. So you select the formula for average and make sure to select all 5 cells and click enter. As you can see, the data is being calculated. So in order to transfer, you don't need to input the formula over and over again for all these 12 samples. Instead, you will highlight all the cells here where the average or mean value is supposed to appear. And as you can see here, there is a fill button here. So it says that you can continue series pattern into neighboring cells in any direction. So you will select the right direction, and as you can see, Excel was able to calculate the average values for all the samples we have here. Also, we need to calculate the standard deviation for these samples. So we'll click equal sign, start typing standard deviation. Make sure to select standard deviation as for samples because we have a small sample size. And it is very important not to select the mean value that being calculated, only the 5 samples that we did, and then click enter sign. Same way we can do the distribution of this calculation over to all the other columns by again highlighting all the cells and then going to fill and going to the right. And as you can see, standard deviation is being calculated for these samples. Now we need to construct the graph to analyze the data. For that, you can click any empty cell and then go to insert and then select the column or bar chart. That's what we're going to use for our analysis, and select the most simple one in our case. Then you want to go to select data and then add the legend entries or series. In our case, the legend entries or series are the two different strains of bacteria, E. coli and S. epidermidis. So by clicking the add button, this box will appear. So for series name, you just need to select the name of one of the strains of the bacteria. In my case, it's E. coli. So as you can see, the name E. coli appears in the box. Make sure to delete the default value of 1, and then by pressing and holding the Control key down, you will select the average values only for E. coli. And then press OK. Next one, the next series or entry that you need to add is the S. epidermidis. So you need to click the add button again. This time for series name, you will select S. epidermidis. As you can see, the name appeared in a box. And then make sure to delete the default value. And then now you will select the average values for S. epidermidis only by pushing and holding the Control key down. And then press OK. As you can see, now the bars appear on a graph, but also as you can see here on horizontal or category axis, instead of the names of the antibiotics, the numbers appear. So to change that, you need to go to Edit, and then again by pressing and holding the Control key down, make sure to select the names of the antibiotics, and then press OK. As you can see, the names of antibiotics appear on the bottom. Then press OK. Also, you need to add other elements of your chart, important elements, such as the axis title, chart title, legend. As you can see, legend is being generated automatically. Your legend is E. coli and S. epidermidis, and it appears which bar represented by which color. Also, very important, you also need to include the error bars here. By clicking here, it will give you the default value, which is not correct one. So in order to enter the correct error bar value, which is standard deviation in our case, you will click here, go to more option, and then you need to do error bars individually for each strain of the bacteria. So let's start with E. coli and then press OK. Then this you will go down to the custom specific value, and then make sure to delete default value of 1. And as you can see here, it shows positive error values and negative error values. Since we don't have positive or negative, we have a range. It's our standard deviation. We will enter the same value twice. So for this purpose, by holding Ctrl key down, we will now select only the standard deviation for E. coli. And we do exactly the same thing for the negative values. And then press OK. Now the actual error bar will appear. So once you're done with the E. coli, you wanna go and do the same thing for S. epidermidis by clicking on the error bars of the S. epidermidis, and then go to the custom specific value and repeat all the steps that I mentioned before for E. coli. Now it's for S. epidermidis. And then press OK. As you can see, now the error bars are actually representing the standard deviation. They're not default 1, which is incorrect. So also here, what you need to do, you need to add the titles for both axes. So your x-axis is actually represented by antibiotics. So you will type in antibiotics here. And y-axis is actually your zone of inhibition. So you will type zone of inhibition here. And it's very important to put the units. In our case, we measure the zone of inhibition or the diameter of these rings in millimeters. So you need to put millimeters in parentheses. And the chart title, you can be creative about the chart title. So you can write something like the efficacy of 6 different antibiotics against two different strains of bacteria. So yeah, you're pretty much done with creating the graph. And now it's time to do statistical analysis. As you can see here, I already rearranged the data here for statistical analysis. So this is the way it's easier to select the data. So I rearrange them in this type of box. It's exactly the same data. I only transferred the values of individual measurements. I didn't, as you notice here, I didn't transfer the averages or standard deviation. So in our case, we want to, since we have two different hypotheses about significant difference about the resistance of these two strains of bacteria, and is there any significant difference of efficiency of different antibiotics. So for in this case, since we have two sets of variables, we will conduct a two-way ANAVA statistical analysis. So just click any cell, make sure to go to the data, and then there is this data analysis button here, but the reason it appears here because I actually enable it. In order, if it's not enabled on your computer, you need to go to File, Option, and then go to Add-ins, and then here on Excel Add-ins, click Go, and make sure the first analysis 2-pack is check marked. So it is check marked for me, and that's why the data analysis appear on my screen, and then press OK, and data analysis should appear here. So you will click data analysis, and then since we are conducting the experiment with two different sets of variables, but however we don't want to see any replication results, so these two strains of bacteria are they're not interacting with each other. The data is not interactive, so therefore we will choose ANOVA two-factor without the replication. So press OK. So here, it's for me, the labels are marked. I want to see the labels. I want to see each variable that is being used is being labeled. Also for the range, make sure to select the entire box is being selected already. Alpha 0.05, it's a very important value. It shows the threshold. This is how we're testing for the statistical significance, and our significance level, it's normally set to 0.05. I will use this default setting, and I will explain the data once I will explain how to interpret this data once the box with the results of two-way ANOVA appears on Excel sheet. Output value range, you want it to appear somewhere, so you just gonna select any area. There is no particular place that you need to do it, so try to select somewhat big square and then press OK. As you can see, the box appear here, and it has the summary of the results here that you can look, both for strains of bacteria and for the antibiotics. But most important values that we'll be looking at is the rows. So let me highlight those, and the columns. And let me use a different color here. So the rows are represented by different strains of the bacteria, E. coli and S. epidermidis, and the columns are represented by 6 different antibiotics. And the value we're specifically interested in is the p-value for both results. So let me highlight those cells. As you can see here, so again, let me remind you, if you remember about the threshold and statistical significance. So let me put again here. Threshold is 0.05. So this is the value that we're using to determine whether our statistical results are significant or not. So as you can see here, for rows, the p-value is above 0.05. And for columns, it's actually below. This is a very small number. So another way of saying, so for rows, p-value is, let me round up the values, so it will be 8.90. And for columns, the p-value is 6.14 times to the 10 to the negative 7, which is a very small number, which is way below 0.05. So, which tells me that there is no statistically significant difference how E. coli responded to different antibiotics versus the S. epidermidis. So basically, it tells me that none of the results for overall all the antibiotics are very similar. So they responded very similar. However, there is statistically significant difference in how effective the antibiotics are. And it's kind of evident here by just looking at the numbers here. You can see that some antibiotics are very effective, such as the caprofloxacin and tetracycline. But however, some antibiotics, such as penicillin, are not effective at all. So make sure that this you include in your report both the table with your raw data, the graph, and screenshot of statistical analysis. So you need to have a discussion of your statistical analysis results in your report. Thank you for watching this video. Bye guys.